Thank you very much, Paolo, for the introduction. I'm Riccardo Forni, and today I present my work called Virtual Cardiac Histology, a densitometric characterization of left ventricle tissue. So let's start with a brief introduction. Paolo already mentioned densitometry, and for us it's a quantitative measurement derived from Hounsfield unit distribution, so we are talking about computed tomography. And then this measurement is associated with tissue absorption properties, so let's mean density. I mean, one of the most famous examples probably is like bone mineral density that is used for bone assessment at the clinical level in bone-related disease, such as the osteoarthritis. But it's not only related to hard tissue. We have soft tissue, and our group have made a lot of improvement in the literature of studying the densitometry from the mid-height, as we already listened from Paolo. And the thing is that soft tissue composition plays a key role in the assessment and the of some pathological condition. And the parameters extracted from these profiles express an outstanding predictive power for some, let's say, heart-related disease. So a question that came in my mind was, what about studying directly the soft tissue in the heart compared to the mid-height? So while I was thinking about it, I said, okay, but then how a normal heart behave under a densitometric point of view? So this is like the first research question. Say, are there differences in age, gender? So then the first thing is to create a baseline model that then we can compare with some model from the cardiac disease. And for our research, we used data from thanks to the Service of Surgical Planning with the Lens-Spital University Hospital, and we decided to use data with the subject, from post-infarction intraventricular septal defect and hypertrophic cardiomyopathy. Why these two pathologies? Because underneath there are some changes in the tissue composition and organization. For example, hypertrophic cardiomyopathy is this abnormal thickening of the left ventricle. Could be both in the septum and in the left external wall, and is associated with this fiber disarray and the onset of fibrosis. On the other hand, the post-infarction VSD is a coronary artery infarction that can lead to a necrosis in the septum that can thin or become to rupture. And so we have two different pathologies that change and characterize the tissue. So the question was, can parameters from an Hounsfield unit distribution detect and measure these changes? So with a small cohort, let's say, 35 healthy subjects, 7 hypertrophic cardiomyopathies, and 5 VSD, we set up a segmentation workflow. So from CT images, we segmented the myocardium, removing the blood pole because we are not interested in like the blood part because it's enhanced with a contrast medium, and we create like the negative of some specimen that we took cylinders from two different regions of interest. The first one is the intraventricular septum, and the other one is the left ventricular free wall. We establish a sample size of 1 cubic centimeter, and we relate the target volume with some, with some parameters from the images, so pixel spacing, space between slices, and the number of slices that we need for that volume. Once we extract all the specimens from the two regions of interest, then we extract some parameters from this distribution. We have 3 groups of parameters. We have like the density, so the Hounsfield unit mean, mode, and median. The shape profile parameters, so Hounsfield unit standard deviation, peak amplitude, skewness, and kurtosis. And the complexity, the parameter is the entropy. Then we fit a linear mixed model on our experimental data to understand the relationship between the two regions, age, gender, and the pathological condition on the measured parameter. We use a stepwise method model selection with the AAC criterion, and the model with the lowest value was selected, resulting in what is written in the slide. So we have gender, region, pathology, and their interaction as a fixed effect. And then we have this random effect to take into account that we are taking 3 samples from each region of interest. So we have some kind of repetition. After that, we used machine learning to understand if there's some kind of predictive power on our densitometric parameters. And first of all, we try to guess the tissue status and the region of interest of the sample, which parameters was given to input. It's called virtual cardiac histology. But then to understand a bit more, we also split the data set in samples from the left ventricular free wall and samples from the intraventricular septum. And then we have to guess the status. We'll see like the result later. So we trained a random forest algorithm with a 10-fold cross-validation. And then we also applied Smote technique for data augmentation to fix class imbalance. Let's move to a bit more result. So like the first result that surprised me a lot is that age was not a significant regressor for our model. So I showed you before, there's no age in our model. And I think that the explanation could be like these 2 charts. There's no, in both region, IVS and left ventricular free wall, there's no a clear trend in of depending of the parameter, in this case, Ansfield unit mean, over age. And also in this case, you can see the line is completely flat. We have a lot of variability in our data, so age is not something that influence our parameter. Going to the statistical analysis, with our model, we found out that only Ansfield unit mean and median showed great significance. So here I report the result for the mean. The result for the mean are more or less the same. If we look at the healthy chart, we can see that there's a great difference between female densitometric measurement and male. But also there's a huge difference among the 2 regions. So this is like the first result of our baseline model. We have to take into account these differences when we describe and compare the model with the pathological cases. Now if we try to do this, the situation here is a bit more tough because we have less subjects, but we can assume for sure that there's an increase of density in for the 2 classes at the left ventricular free wall. This means that there's 2 pathology that change the let's say the pumping function of the heart. This heart is not working in the best way anymore, and this is the result. Like the left ventriculum need to adapt and pump with more strength if you want to spread the blood outside the heart. And so here we can see like the on the left ventricle, like the values are higher. We cannot say too much on the septum because of the high standard deviation of our data. Here in the table, I reported all the let's say the comparison with in bold the p-value lower than 0.05. Let's move into the machine learning. Here are some results and some metrics, so sensitivity, specificity, and accuracy for the 3 cases. And these data, these results are super good, let's say, but then we have to take into account that we use Smote, so there's a kind of bias in this result. But I think that the most interesting part is the feature importance, showing that in the 3 cases, there's some changes. So let's start with all the data set. We have peak amplitude as first, and then we have some Ansfield units, standard deviation, kurtosis, and skewness. So meaning that the shape of the profile is the most important thing to look if you want to predict the status of the sample from your heart, from your structure. But things changes, at least a bit, when you look at only the septum. And here, the thing that I love, there's entropy. So, as I said before, one of the characteristics of the pathology is that there's like a reorganization of the fiber. There's a kind of disorder. So something that is not more, let's say, optimal. And entropy measures the complexity of the pixel distribution. So here, entropy is something important. So this is a proof that there's something behind the image in the distribution of the Hounsfield unit. While if we look at the left ventricle free wall, the 2 out of 3, the most important parameter, are something related to the mean and the median. So we have a shift in the profile. Let's say that something becomes more dense with the two pathology, and is a proof that is there's something behind. So to sum up, our baseline model shows that age does not affect our parameter, and the female tends to have higher densitometry value on the two regions of interest. There are some proof of changes in the densitometry of the left ventricle free wall, especially in the mean and median, when we compare the healthy class with the two pathological classes. From the machine learning analysis, we can say that the peak amplitude results in being the most useful parameter, but there's some sign of entropy and standard deviation to reveal some change from the intraventricular septum. And to look forward to this, we can use one day, hopefully, this parameter to improve the diagnosis of this kind of disease that are related to the tissue composition. So, as a future development, we want to enrich our data set to get more pathological subjects to prove on a larger scale if these parameters are able to predict the status. But also we want to include frequency pattern from image analysis and also texture analysis from the images that can really give us more information about the spatial organization of the pixel. Or furthermore, we can investigate the composition, looking at inside our cylinders, if with some different thresholds we can find out if fat, muscles, or other denser structure can be detected. So that's all. Thank you very much for the attention.